All right, students, I wanted to do a couple of videos on, or a couple examples on limits as x approaches infinity or negative infinity. And the idea there is to compare, you usually have a rational function, and you want to compare the numerator and denominator. And the reason it works is you can use the properties of limits to get rid of all of the smaller terms, and you really only have to compare the leading terms of the denominators and the numerator. So here's a quick example. If we're looking at limit as x approaches infinity of 3x over x plus 3, what I can do is multiply the top by 1 over x, multiply the bottom by 1 over x, and then the top becomes, I'm allowed to do that because x is not equal to 0. X is approaching infinity, so I'm not running into any discontinuities. So I get 3 over 1 plus 3 over x. And then one of the properties of limits is that you can apply the limit to the top and the bottom of a fraction separately, so long as the bottom limit is not 0, because then you can't divide by 0. So then I go to the limit of the top, which is just 3, and the limit of the bottom, which is just 1 plus 0, because 3 divided by a large number gets closer and closer to 0 as the number gets larger, and so the value is 3. Now, many people will just shortcut it and notice that the ratio of the leading terms is 3 over 1. But the reason that it works is the properties of limits, that you can apply the limit to the numerator and to the denominator, and then you can distribute the limit across addition. So that's the first example. I'll do one that's a little bit harder. That was question 2a. This is question 2c. So we'll do the limit as x approaches infinity. We've got negative x squared plus x plus 2 over 3x squared plus 2x minus 1. Multiply top and bottom by 1 over x squared. Again, I'm allowed to do 1 over x squared because x is approaching infinity. I'm going to distribute it. So I have limit as x approaches infinity of negative 1 plus 1 over x plus 2 over x squared. And then that's 3 plus 2 over x minus 1 over x squared. And then a lot of stuff just equals 0 here. If I do the limit as x goes to infinity, this becomes 0, this becomes 0, this becomes 0, this becomes 0, and I'm just left over with the ratio of the leading terms, negative 1/3, so that's the limit. Notice that it really matters what the degree is of the top and the bottom, so it matters what the biggest exponent is, because that determines which terms are going to tend towards 0 and which terms are going to survive as you apply the limit as x goes to infinity. So a little bit harder of one would be 2h. So let's look at the limit as x goes to infinity. Let's do the same sort of trick, just looks a little different. Square root of 4x minus 1 plus 2 times square root of x plus 3 over square root of x. Let's multiply by 1 over root x times 1 over root x. Same reason as before, that's okay to do. That's going to make the denominator equal to 1. And then the numerator here becomes square root of 4x minus 1 over x plus 2 square root of x plus 3 over x. And I'm going to try to squeeze this in at the bottom, that we can make this the limit as x approaches infinity of square root of 4 minus 1 over x plus 2 times 1 plus 3 over x. Same idea now. We can apply the limit as x approaches infinity, getting 0 for this value, 0 for this value, leaving you with the square root of 4 plus 2. So your final answer is just 4 there. So you can shortcut it. If you noticed that the top and bottom had the same degree, they both have the 1/2 power, and the top has a leading coefficient of square root of 4 and 2. So that's how you get the 4 there. The only other example that I really should show is one where the denominator has a higher degree. So maybe 2f, where we're looking at x minus 1 over x squared plus 3x minus 2. I'll multiply by 1 over x squared on the top and the bottom. So I have 1 over x minus 1 over x squared. On the bottom I have 1 plus 3 over x minus 2 over x squared. And then as I apply the limit, I get 0 minus 0 over 1 plus 0 minus 0. So it becomes 0 over 1, which is just 0. I skipped writing the limit there, but you really should make sure that you're writing the limit as x approaches infinity in order to justify what steps you're doing, because it's not true that those expressions are equal unless you write the limit there. Okay, so if the denominator has a higher degree than the numerator, your function is going to tend towards 0 as x goes to infinity. Just real quick, graphically, what that means is as I go really far to the right, my function is going like that, or possibly coming up from the negatives. So the value y equals 0 is called your horizontal asymptote. So that's just a nice connection if you're looking at the graph. Okay, thanks for watching. Please comment or ask questions if anything is confusing.